For this chapter, it is talking about the polarity of bond and then the polarity of molecules. We have to know that if the bond is polar, then it may affect the molecules to be polar, but it is not a must. We will think about the case. However, we start with the polarity of bond first. For the polarity of bond, we think about when two identical atoms, for example, two hydrogen or two chlorine atoms sticking together to become molecules, H2 molecule or Cl2 molecule. The bonding electrons are shared equally between the atoms. They are shared equally means they are placing in the middle for the shared electron. So are the bonding electrons also shared equally between two different atoms? Like if it is two different atoms, we need to decide about by the electronegativity of an atom. Bonding electrons may not be equally shared between two different atoms. One atom may attract the shared electrons more than the others. So we need to consider about the electronegativity. In general, an atom with a higher electronegativity will attract the electrons closest to itself. So the electronegativity represents something. So for an atom, the electronegativity represents the power of that atom in the molecule to attract the bonding electrons. So it is related to the power for the attraction of bonding electrons. So we have a term called Pauling scale or Pauling's electronegativity scale. Paulings assigned different values to the atoms of the elements. As a result of that, it has a table about this. Like for example, lithium is assigned the value to be 0.98, while fluorine is the 3.98, or hydrogen, it is 2.20. You don't have to remember about those values. However, in general trend, we will talk about later, you have to know about that. However, you don't need to know or remember the specific value of H is equals to 2.20. Although it may be good for you to remember some of them. However, it is not a must to remember those values. But the electronegativity values show us what? The ability or the power of that atom attract electrons, especially for the bonding electrons. So let's take a look for this one, this arrangement instead of the 2D version. Like you can take a look. Like for example, lithium, the group 1, we neglect the hydrogen first. The group 1 metals, in general, you can see the trend, it is stepping down. That is the electronegativity is going lower and lower. While across a period, lithium, beryllium, boron, and carbon, nitrogen, oxygen, fluorine, it is stepping up and up. That is the highest electronegativity value should be fluorine, while the lowest one is lithium in period 2. However, for the group 1, lithium is the highest electronegativity, while cesium is the lowest. Like, you have to know about some reason. Like, you can think about that it's related to the number of proton inside. So, for example, for fluorine, it has 9 protons altogether, while lithium is just get 3 protons. Now, for this one, that means if it is bonding with the hydrogen, then the ability of attracting the bonding electrons will be different. Because here it has 9 positive charge, it attracts the electron closer to the fluorine atoms, that is closer to the more proton side. While it's just got 3 protons, if it is the covalent bond, it doesn't want to attract the bonding electrons. Now, although lithium, we know that it is not a covalent bond with hydrogen. We still regard it as the covalent bond first in this case. That is, 3 protons, it has less ability to attract the bonding electrons towards itself, while now proton, it has more ability, higher ability to attract the bonding electrons towards itself. Just the same case if for fluorine to iodine. So fluorine is just got two electron shells used, that is purity 2, while iodine, although it has more number of proton, but it has 5 electron shells. So we need to add one more as well. So that is if it is experiencing the attractive force for the outermost shell, it has a lot of electron shells penetrate. So as a result of that, iodine has a least electronegativity compared with the two shell stuff, which is fluorine. That's why this is the general trend for the elements. We found that the most electronegativity element is fluorine. It has assigned value is 3.98, and some of the time we will say that it's 4.0, while the least electronegativity elements, it is in the group 1 bottom, it is the francium, and the electronegative value, it is 0.70. So we have the general trend here, the increasing electronegativity across the period, while the electronegativity values will be decreased, say in the same group. As noble gas didn't form any chemical compounds or bonding with other elements, we don't assign any value on the electronegativity of the noble gas. So for the bond polarity, when an atom are identical electronegativity, they form covalent bond. That means the power of attracting the bonding electrons are the same. As a result, they share the electrons equally. That is the case of hydrogen. So we say that the bonding, the covalent bond, is nonpolar. Well, if it is different electronegativity atoms, they form a covalent bond, then the bonding electrons are not shared equally. The polarization occurs. For example, here, with hydrogen, they have same electronegativity. They share the electrons equally. As a result, it is nonpolar. However, for HCl, we found that chlorine has the higher electronegativity. It has 3.0, while hydrogen is just got 2.2. As a result, the bonding electrons ability, the attraction of the bonding electrons for chlorine will be higher. Hence, the bonding electrons rather go to the chlorine side. As a result of that, we say that it is a delta positive and delta negative, because originally the electron should be placed in the middle. Electrons bear negative charge, while the electrons shift to the chlorine side. As a result, it has a partial negative, that is delta. A little bit means, delta means a little bit. That bears a little bit negative because the electron's density is higher in chlorine side. While we left the chlorine, we don't have chlorine left on the hydrogen. As a result, there will be delta positive. We say that this is non-polar bond in hydrogen, while a polar covalent bond for hydrogen chloride. As the more electronegativity atom has a greater share of the bonding electron than the less electronegativity atom. So we say that here, the hydrogen chloride, it is a polar covalent bond presence. The more electronegativity atom has a partial negative charge, which the less electronegativity atom has a partial positive charge. We will use the sign delta. It's just like D, while it's just like drawing a signal like this way, delta means. So we assigned the value, the delta positive, to the less electronegativity element, which is hydrogen. While the chlorine, it is more electronegativity, we assign it as delta negative. So the covalent bond is said to be polar. While delta positive and delta negative, or we say that delta plus or delta minus, respectively. Delta is used to indicate the charge is very, very small. It is not absolute positive or negative like the ions, cation or anion. It's just got a little bit charge. As a result, we say that a very small charge generate. The polar hydrogen chloride represent like this way, delta positive, delta negative. In general, when the electronegativity difference increase, then the polarity of a covalent bond will be increased. So for electronegativity difference, if they are the same atom, for example, hydrogen and hydrogen, they don't have any electronegativity difference. As a result of that, then it will be a non-polar covalent bond. However, if it is a polar covalent bond, we will see that the least polar atom, the less polar atom will be delta positive, while the more polar atom will be delta negative. You may think about some of the case, you may pause it and think about some of the case, which one is this AB will be? The answer will be here. For example, if bonding is carbon and then sulfur, carbon has 2.5, S has 2.5. If they form a covalent bond, then it will be non-polar. However, for this one, AB, we form a polar covalent with A is delta positive, B is delta negative. So what is the case? It may be hydrogen and then fluorine. This is one of the example. Maybe some of you will think about whether it is suitable to be Na or F. Now, for this case, Na, the difference of the electronegativity, one is 0.9, fluorine is 4.0. As the electronegativity difference, we say that's the delta En, the electronegativity difference, greater than 2.0. As a result, it will become ionic already. It is no longer partial charge here, not delta, no longer delta. So if you use sodium, potassium as an atom here, then it will not be the case. However, if it is hydrogen or chlorine, it is also the case. So one is 2.1 and other one is 3.0. And then because chlorine has a higher electronegativity, then the electrons will shift to the B side, that is the chlorine side. We say that we will use is an arrow to showing that the electrons is shifting to the B side, the atom B side. So we will draw like this way, just like the bonding electrons going to the B side. But the details of this kind of arrow, we don't need to know about that. So that's why a covalent bond, if it is equally shared for the bonding electron, it should be non-polar. While if it is not equally shared, a covalent bond is started to be polar. As a result of that, when we see or when we read about the table, you will find that when the atoms are identical, hydrogen and hydrogen, no electronegativity difference, so we say that it is non-polar. While HF, the electronegativity difference will be greater because fluorine has the highest electronegativity value assigned to it. As a result, the electronegativity value will be higher. We say that it is the highest polar bonding, but this is non-polar at all. Now, it is just like a continuum. It is generally increased when you are having the different atoms there. Hydrogen and sulfur, the electronegativity is 0.38. Hydrogen chlorine, 0.96. Hydrogen and oxygen, 1.24. That is the increasing polarity of the polar bonds occur. So that is the case between the relationship of the electronegativity difference and the bonding polarity. So that's the end of the 25.1.